Hello, Math 1224. This is Dr. P with Lesson Launch 17.1. Guess My Polynomial. In this lesson, we're going to be starting with Chapter 10 in the Hughes Howlett textbook. Now, we just finished a section on power series, and Chapter 10 is sort of a continuation of that. But the first thing that we do in this chapter is we change the subject a little bit and talk about the idea of how we can approximate functions whose derivatives are known at a point using polynomials. So that's why we're calling this Guess My Polynomial. Is what we're going to do in this section is we're going to take a function with some given information at a point. So for example, these function values and derivatives here. So we're going to take that information as given, and we're going to develop a polynomial that satisfies those conditions. And the idea is that, well, I'm given some function f that has these four pieces of information, this function value and three derivatives at the point x equals 0. Now that function may or may not be a polynomial, but if I could create a polynomial that has these four, that satisfies these four conditions here, then that polynomial would probably behave an awful lot like f near the point x equals 0. So just write some of this down. I always feel like writing on this thing during a video is awkward because it takes forever to write. But here's the idea. The idea is we're going to create a polynomial p with the same value and first through third derivatives at x equals 0. And then what we hope for is that this polynomial p, this polynomial p, will then be close to f near x equals 0. And why would that be the case? Well, why would it be, if I were to create some polynomial p that satisfied these four conditions here, why would it be close to f? Well, it would have the same value as f at x equals 0, so f of 0 would be 3, and p of 0 would also be 3. It would have the same rate of change. It would have a rate of change of 1 at x equals 0, so it'd be changing at the same rate. And its rate of change would even be changing at the same rate. Its second derivative would be the same. And if you don't like that, then you also know that the rate of change of the rate of change of the rate of change would be the same. I think I got that right, the three of those. So if you know all of those things, then goodness knows, the polynomial p might not be exactly the same as f, but it ought to be pretty darn close, as long as we're close to x equals 0. So that's what we're going to do in this video. I'm going to zoom out a bit, and then we're going to do some mathematics here. So let's just first take a very rudimentary first guess. First guess. And I'm going to let p be, let p be a constant function. That is an example of a polynomial. A constant function is polynomial. It's the most elementary kind. But I might say, okay, let's let p, I'm going to call this p sub 0, because I'm going to do several iterations of this. Let p sub 0 of x equal just 3. So consider the polynomial that is always equal to 3. All right? Then that might be an okay approximation for f locally, but eventually there's going to be some problems, because I know based on the info above that my function value, let me use blue for that since I put that info in blue. My function value for f is going to be 3 when x equals 0. The derivative is 1, so I know that I have there a tangent line of slope 1. And I also know that because the second derivative at 0 is positive, in fact very positive, I'm going to have some concavity. It's going to be concave up. So I should expect my graph to look kind of like that around x equals 0. Now I'm just guessing there. But what I'm doing now with p0 is I'm approximating that. That, by the way, was f. And I'm approximating that with a constant polynomial. It's just equal to 3. And I don't know, that's an okay approximation near 0, but it's not very impressive, and it's something that we could have done without knowing any calculus. All right, so that's a first guess, but that's just kind of a straw man that we're going to knock down and improve. Anyway, let's try for a second guess now. Second guess. Let's let p I'm going to call that P0 and this P1. Let's let P1 be a linear function. All right. So I need to think of some linear function such that P1 of 0 will be 3, same as f of 0, and such that P1 of 0, P1 prime at 0, sorry, will be 1. So in other words, I'm gonna force this linear polynomial to have the same value and the same first derivative at x equals 0. All right, can you think of a polynomial that that has the value 3 at x equals 0 and has derivative 1? I think I can. I think that would be p sub 1 of x equals, and I'm going to go ahead and let it have a constant term of 3. There we go. And then a linear term of x. And I think that that would satisfy both of these conditions here. I know that then P1 of 0 would be, I'm just verifying this, P1 of 0 would be 3. And then P1 prime at 0, sorry, that's 1 prime there, that would be equal to, well, the derivative of P1 is just 1, and that's 1 everywhere. So this polynomial has the same value and the same first derivative at x equals 0. So I'm hoping this might be a better approximation for f. Let's graph what that might look like. Now again, all the graphing I'm doing by hand. You might be able to do a bit better if you had a computer and had some formula for f that you could plug in. Well, we don't quite have that advantage here. But again, f has f of 0 equals 3, and has slope of 1 and has some concavity. So again, I'm really just guessing about what that concavity looks like. But I think in this case, P1 is going to have the same value and the same slope, but not the same concavity. It's just a linear function. So this is now P1. And you can see that that's probably a better approximation near 0 than P sub 0 was, but it's still not the best we could do. So let's see if we could do a little bit better now. So for my third guess, I'm going to let P2 be a quadratic function. So this time, last time I was able to just come up with a linear function just right out of my head that had the right function value and the right first derivative at 0. Now with quadratics, I'm just not as confident that I can do that. So I'm going to write down the conditions that I want to satisfy. I want P2 of 0 to still equal 3, P2 prime at 0 to equal 1, and you might recall from up there that my second derivative of f at 0 was 4. See, I made the numbers easy to remember, 3, 1, 4, 1. And then if I'd had another derivative, it would have been 5. See? Anyway, I want the second derivative at 0 to be 4. So how am I going to create a quadratic function that has all three of those attributes? Well, I know that P2 of x needs to equal, and I'm going to take a really naive approach here because I think the constant term still needs to be 3, but let's just suppose that I start from scratch here, and I say, well, the only thing I know about a quadratic function is it has to look like this. It has to have a constant term, a linear term, and a quadratic term. And that's all I know so far. All right? And let's think about how we might force these coefficients to match. So I call this the method of coefficient matching. And this comes in a lot of problems. You might have at some point fit polynomials to data using this method, or fit exponentials to data. This is kind of the same idea. We're going to use coefficient matching to try and get C0, C1, and C2 to have the right values. The way I'm going to do it is I'm going to work backwards from this. I know that my function has to look like this, so I'm going to check that versus this data here by actually calculating those derivatives. So P2 of x, P2 of 0, I know P2 of 0 is just going to be C0. That's what P2 of 0 is. If I substitute 0 into this formula here, then all I get left is just this dude, C0. I know that P2 prime at x, just by calculating the derivative, that's going to be C1 plus 2 C2 of x, or C2 times x. So that means that P2 prime at 0 that should be just C1. And then P2 double prime at x is going to be, now I'm just taking the derivative of this thing here. Second derivative should be just the derivative of the first derivative. P2 double prime at x is just going to be 2C2, just the derivative of the thing above. So that means that P2 double prime at 0 is going to be 2C2. So now if I just come over here, give myself a little more room to work, I know that I wanted P2 of 0 to be 3. So if I look at this and match it against this, I needed that to be 3. So that tells me that C0 needs to equal 3. And I wanted P2 prime at 0 to be 1. So that means that C1 needs to be 1. And finally, I wanted P2 double prime at 0 to be 4. So I need 2 times C2 to equal 4. That means C2 has got to be equal to 2. And I'm just going to write that as 4 over 2, because that might be a useful reference point to have later, just something to remind ourselves how we wound up at 2. Anyway, so that means that my P2, it looks like the optimal quadratic function for me to use would be P2 of x equals 3 plus x, that's C1x, plus C2x2, that's plus 2x squared. Sorry, x squared. So that means that my quadratic approximation to this function is going to look something like this. Now again, this is f. F starts at 3, has slope of 1, and has concavity. There we go. And then P2 of x, that's going to have the right value, the right slope at 0, and also the right concavity. So it's probably going to do something like this. Now, you'll notice I've drawn it so it's not exactly flush with that function graph. And honestly, I don't know that it wouldn't be. Well, I actually do know that it wouldn't be, because they don't have the same third derivative at that point. But aside from that, I can't really quantify how far off those are going to be from each other. I can just tell you that P2 is going to have a parabolic graph that very closely matches the graph of f near x equals 0. All right, so that's a pretty good approximation, but I could do even better. So now I'm going to look at the best fit cubic function at x equals 0. So let's see, I think I'll just come over here. So this will be my fourth and final guess in this video. This is starting to get a little bit cumbersome here. So let's try P3, a cubic function. Well, P3 of x is going to be, it's going to have this form. And by now, you should probably be guessing that C0, C1, and C2 are known. They're just the same things I got earlier. And you can actually do the mathematics. You can find the derivatives and discover that that's exactly right. I'm going to go ahead and find the derivatives again, just because the tail ends of these look a little bit different. All right, P3 double prime at x is going to be 2C2 plus, let's see, 6C3x, and then P triple prime at x is going to be, I believe it's just 6C3. So you'll recall that I want these values here at 0. At x equals 0, I want these to be 3, 1, 4, and 1, respectively. And what's going to actually determine the value of these things, those are going to be these coefficients here, because all the other coefficients, or sorry, all the other terms at x equals 0, they just go away. So that means that I need C0 to equal 3, C1 to equal 1, C2 again to equal 4 over 2, and then C3 to equal 1 divided by 6. So my best fit cubic polynomial would be 3 plus x plus 2x squared plus 1/6 x cubed. Actually, I'm just going to step back here and rewrite that 2 as a 4 over 2, because actually there's a general principle that I want to illustrate here, which I'll probably just have to get to in the next video. This is already quite a bit longer than I'm comfortable with. But that would be the best cubic approximation to f near x equals 0. And again, like what we were talking about in class, That does not mean that this is a perfect approximation for f. It does not mean that it matches the value of f exactly, except at x equals 0, where it has to have the same value. Beyond that, it might have a different value, but we hope it would not be very far from the actual value of f. Okay, so anyway, in the next video, I will talk about how we generalize all of this. Stay tuned.